Hello, everybody. Professor Monty here. Today we are going to talk about section 4.3, area and definite integrals. So first of all, let's just start off. We'll just do a random function here. And suppose I've got a function, and we will just call this function f of x. And what we're going to do is we're going to look between 2 points on the function a and b. And what we're going to do is we're going to look at this area in between a and b. Well, remember, we saw last time the area under the function is equal to the total change in the function. And so what we're doing here, we're talking about definite integrals. This area right here that we've highlighted, we can write as an integral from a to b, f of x with respect to x. So when we write this here, what we're doing is we're saying, okay, I've got some function, f of x in this case, and the area under that curve evaluated from a to b, this number a on the bottom is always on the left, and the b is always on the right. And what that's going to give us, that's going to give me that total area under the curve, which is the total change in the curve between those two places. So we're going to use that. In this section, it's all about this integral that I've written here from a to b of f of x dx. We're going to talk about what that actually is. And we're going to start off, it's called the fundamental theorem of calculus. So we know it's an important thing just by the name of it. But let's do this. Let's get this out of the way. And what I'm going to do is I'm just going to put the whole function here for you to see. So let's go grab that. I'm just going to paste it in here. And we'll take this. Let's write it this way. We're just going to copy that down, and we'll just paste it right in. Okay, so that you'll have it in your notes. Okay, so the fundamental theorem of calculus. I write it a little bit different than they do, but what they're saying is if a continuous function f has an antiderivative capital F over the closed interval a to b, where n is the number of subdivisions of the closed interval a to b. So remember last time when we took an interval, so we may have taken this interval right here, and what we did rather than saying we're going to take those, what we did last time, remember we did, well, that's not going to be up that high. Let's erase that piece. We took left endpoints, and we went up to that height, and we made a rectangle. And we went up to this one, and we made a rectangle. And this point, we made a rectangle. And we did that same idea all the way across. I want it to be a little bit higher. And the area of these rectangles would approximate the total area. Sometimes the rectangles go a little above, sometimes they go a little bit below, so they're not exactly that area because this green curve is a curve, not a straight line. Okay, so we did that. That's what this is doing. This down here is adding up all of those rectangles. Well, if I take the limit as the number of rectangles I put in there approaches infinity. So think we're getting more and more rectangles, so we have to make them smaller and smaller and smaller, thinner and thinner. So eventually they're paper thin, and each rectangle, essentially, if I draw it, I've got a rectangle here, and I've got a rectangle right next to it. I've got a rectangle right next to it. And so there's really no gaps in between because they're just the width of a line, and it can go straight up to wherever the function is. So eventually I'm actually filling in all that area exactly, and I don't have any gaps. All this is going to be filled in exactly up to the top. And that's enough. We get the idea of what we're talking about there. So that area is going to become exactly this definite integral. Now, I like to write the fundamental theorem a little bit differently because notice what they say. They're saying the integral of f of x, where here it's this there's an antiderivative of capital F. And when I looked at that, it always confused me. So I like to simplify it a little bit. I like to write it this way. We've got the integral from a to b, but this thing that we're taking the integral of is the derivative. And then if I take the antiderivative of that, well, we know the antiderivative of the derivative is just the function itself. I would evaluate it at b, and then I would evaluate it at a. So now I don't have to worry about what's capital F and what's, oh, so if this one on the left, this integral of f prime, then I go back to the original function and then I plug in b and a. And we know that makes sense because consider, for an example, say that we were going from 10 to 50 of c prime of x dx. So say we're talking about marginal cost. What this is going to be, it says, hey, if I've got the marginal cost function, what's the total cost to go from 10 units to 50 units? And so think about how I would figure out, well, here, let's write that out. So this is going to represent total cost of increasing from 50 units, from 10 units. Well, that didn't come out very well. From 10 units to 50 units. And we all know how we would do that in general. In general, we'd say, okay, what's the cost of 50 units minus the cost of 10 units? And that difference is going to be the change in the cost or the cost for those 40 units. This is exactly, let's do that in blue. This is exactly what we're saying here. We go to the original function at the top value minus at the bottom value. Well, that's how we would figure out the total cost from going from 10 to 50 units. If we find the cost at 50 units minus the cost at 10 units, and that difference is the in between. So that's all that fundamental theorem is. So I'm going to box this in green. This is the way I think about it, because then I don't have to, I always get confused. What's capital F? I don't know what capital F is, but if I write it as f prime, I know, oh, that's the derivative. So then we're going back to the original function, which makes sense because that's what we talked about last section, is we're taking the antiderivative, the integral of the derivative. Well, that antiderivative of the derivative cancels out the derivative, gives me back the original function. So that's what we're going to do. We're just going to do a bunch of examples here. But what we're going to get as an answer represents, you can think of it one of two ways. It's the total change in the original function, or it's the area under the curve. So we can look at it either way. Now, let's jump in. We're just going to do a few problems. I'm going to start off. We'll get this. We'll move this up. And I'm going to do some problems out of the book. Again, it's problem number 2 in the book, but if you have a different edition of the book, it might not be number 2. So they give us the function y equals 5. And then the question says, find the area under the given curve over the indicated interval. And the interval they give us is 1 to 3. So the instructions are find area under the curve over indicated interval. So let me draw you a quick picture of this. So let's see, we've got the function y equals 5. So here's x, here's y, here's the line y equals 5. And what I'm trying to do is I'm trying to find the area between 1 and 3. So it's this area right here. Now last section, what we would do, let's put a 5 right here so we know that's the height. Last section, we'd say, oh, it's the area. That's just a rectangle. I know the integral, so we can write it one of two ways. The integral, I don't want to use blue. I want to go back to black. The integral from 1 to 3, right? Here's our a and our b from 1 to 3 of 5 with respect to x. That's how we write that. We know from before this area is length times width. Well, this length here is 2. 3 minus 1, 2. Width here is 5. So we have 2 times 5. Oh, I know, that's 10. That's the area. That's what we did last section. Well, this section we're saying, oh, the fundamental theorem says that area is the same as the definite integral. So I can come up here and I can integrate that 5. And remember, the integral of 5 is 5x, because the derivative of 5x is just 5. And I'm going to evaluate it. The way we write that is from 1 to 3. And then what we do is we plug in that top number into this function right here. Well, it's 5 times 3. And then we do minus, and then we plug in the bottom number. Oh, so it's 15 minus 5, which miraculously is that same 10. So these, of course, are the same values. And so that's what we're doing. Notice we can find it as an area, or we can find the definite integrals, what they call it, once we have those limits of integration, the 1 and the 3. Either way, we're going to get the exact same answer. Now, we could do it either way as long as we have a nice linear function, as we did in problem 2. But remember, if we have a curve, I can't find the exact area. I had to approximate it with rectangles. The fundamental theorem says we don't have to approximate with integrals. We can just plug it in using the fundamental theorem and find the answer right away. So let me show you another example. So here's problem 6. It says the same thing. I'm not going to write the instructions again, but they give us y equals x cubed, and we're going from 0 to 2. Now, let me show you this picture. The graph of x cubed over here looks like this, over here looks like this, but we're going from 0 to 2. Well, so here's 0. These are supposed to match up right here. There we go. That looks a little bit better. We're going 0, 1, 2. We're trying to find this area right here. Again, we can't do that using rectangles because they wouldn't be at the same height, no matter how tall those rectangles are, unless they're infinitely thin, which would mean we'd need an infinite number of rectangles. But the way I find this is I just use the fundamental theorem. I say, oh, that's just the definite integral from 0 to 2 of x cubed dx. And now I can find that just by working it out. Remember, add 1 to the exponent, multiply by the reciprocal. Here's the good part. We don't have to put plus c. I'm going to put plus c here on this problem and show you that we never have to do it again. So say we were doing this, and we were going from 0 to 2. Remember, I plug in the 2 where the x is, and then I go minus, and then I plug in the 0. So I would get, in this case, 1/4 times 2 to the 4th plus c. And then I minus, and then I plug in the 0. 1/4 0 to the 4th plus c. And notice what happens. First of all, I square the 2. I raise 2 to the 4th power, excuse me. So I get 2, 4, 8, 16. 1/4 of 16 is just 4. Plus c. Minus, well, 0 to the 4th is 0. Times 1/4 is still 0. Plus c. And then if I drop the parentheses, I have 4 plus c, but that minus distributes in to get minus c, and I just get 4. The constant's not there. It cancels out. From now on, anytime we have a definite integral, so we have these limits of integration, 0 to 2 in this case, I never have to put plus c on those. I have to put plus c if I don't know the function, because the constant could be any number depending on what they tell us. But with a definite integral, remember there's no plus c, because what we're looking for, this 4 is the exact area. So the exact area can't be plus some c, some constant. It's just that area. And that area under the curve down to the x-axis is exactly 4. Okay, So those are working pretty nicely. Let's do one more quick example. And then we'll look at some pictures. So here's problem 12, y equals 2 over x. They don't give us this picture in here, but they say we're trying to evaluate from 1 to 4. I will show you the picture. The picture looks like this. It's a 1 over x graph. It looks like this. Actually, it's 2 over x, but well, that's not quite as nice as I'd hoped. So we're coming, it's something like this. It's got horizontal asymptotes at the x-axis, a vertical asymptote at the y-axis. We know there's a vertical asymptote at the x-axis. I think I said that wrong. There's a vertical asymptote at the y-axis because if x is 0, that's 2 over x is undefined. Well, so x equals 0, which is the y-axis, is a vertical asymptote. So anyway, but what we're trying to do is we're trying to find the area between 1 and 4. Well, if I go 1, 2, 3, 4, it's this area right here. I'm trying to find this area. And you don't have to draw it. There's no, if you're thinking, oh, I don't know what this graph looks like, that's fine. Because we don't need the graph, we're just integrating 2 over x dx from 1 to 4. Now be careful. Remember that x on the bottom means x to the negative 1. I can't add 1 to that exponent and divide, because if I add 1, I get 0, and then I have to multiply by 1 over 0. That doesn't work. Remember, I can pull that 2 out front, and it's 1 over x dx. And remember, what has a derivative of 1 over x? That's the ln of x. So when I do that, it's actually 2 times the ln of x. We do the absolute value, and we're going from 1 to 4. By the way, here's why we do the absolute value. Because if this problem was, say, -1 to -4, we'll call this an aside. If this was the integral -1 to -4 of 2 over x dx, well, now what's happening, we have the same graph. That didn't come out very well, did it? I tried to draw it real quickly and it wasn't very nice. Let's see. I'm having trouble with my angle here. All right. Oh, that didn't help very much. Here we go. Let's move that up. That'll help. Okay. So there's my graph. What I'm looking for is from -1 to -4. So from -1, 2, 3, 4 to -4. In this case, I would be looking for this area. Well, the area still exists. I'd still be able to plug the -4 and the -1 in for the ln of x. But I can't take the ln of a negative number that doesn't exist. That's why I take the absolute value, because now it'll change those to positive arguments. The -4 and the -1 become +4 and +1. Then I can take the ln and I can still find the area. So this whole aside just has to do with why we do ln of the absolute value of x. That's why we do the absolute value, is because that area is still there, but we wouldn't be able to plug it into the ln otherwise. So anyway, on this one we go L2 times, now it's this whole thing, it's ln of the absolute value of 4 minus ln of the absolute value of 1. Since those are positive, the absolute values don't do anything. But that's my exact answer. And I'll give you a hint, ln of 1 is actually 0. So as an exact answer, they may just write it as 2 ln of 4. You don't need the absolute value anymore because 4 is already positive. So that's the exact answer. But if we plug that into our calculator, let's see, 2 times ln 4 to 3 decimal places, I'd get 2.773. We'll say approximately 2.773. That's my approximate answer. Okay, so depending if they want the exact answer or the approximate answer, either way, that's what we get. So again, here's another example, but the fundamental theorem, again, we don't need the picture. I like to put the picture because I think it helps us figure out what's going on. Let's put a 1 and a 4 here so we know what we did. But so that's the idea. Okay, so let's go from there. Let's go to another idea from here, and I'm actually going to put another picture in here. Let's see, we'll put it about right there. Let's see. So there's a couple pictures in here I want to do, and it's back to the idea that the area under the curve is, well, what it represents. So let's put this in here. So we'll go here, I'll just paste that in. Okay, so we've got a couple problems here. And so let's look at these. The question says, explain what the shaded area represents. So notice on this first one, so here we'll write that down. What does the shaded area represent? All right, there's my question. And so let's answer it. This area, now notice the curve is, it says cost in dollars per day. Well, if it's in dollars per day, that's the marginal cost. That's actually C prime of X. It's the marginal cost. And remember, we talked about last time, what's the area under the marginal cost? It's the total cost. In this case, the total cost for T days. So the curve was marginal cost, but the area below it is the total change in marginal cost, which is total cost for T days. What are these? Small case. And then in the next problem, think about what they're saying. Number of kilowatts used per hour. So this curve is in kilowatts per hour. So it's the rate of change of kilowatts. So the area underneath is total kilowatts used. In T hours. So just realize if it's the area under the marginal, again, that's marginal because it's kilowatts per hour. When we go to the total, it's not, notice it's not total kilowatts per hour. The per hour is gone. It is just total kilowatts. Okay. So that's the idea. The area under the derivative is the total change in the function itself. Because here's an example with the cost. Say that the marginal cost right here was $5. Well, if that unit cost $5, that added $5 to the total cost. And then this unit costs $4. Okay, so now we've got $5 for the first one, plus $4 for the second one, and then plus another $5 for the next one. We would just add all those up. And once we add all those up, what it represents is the total cost. So that's the idea. We'll erase that. But that's why it's always total of whatever that marginal was representing. Okay, so now from there, what I'm going to jump into, this is going to kind of be related to this with the area, but it's something we haven't seen with the integrals yet. So I'm going to put another picture here. So let's go back into my files. I'm going to plug in mine it's problem 34, A and B. In your book, again, it might be something else. It doesn't matter what number it is in your book, just so that we understand the idea. So let me paste this in. Okay. Now this problem, now in the new edition of the book, it's problem 34. In the old edition of the book, it's 34 also. So this one was the same, but some of them are different. That previous problem I did, that 16 and 18, in the previous edition of the book, which if you bought the book, let's see, the cost in dollars per day, that was actually problem 15, not 16. And the kilowatt one was problem 17, not 18. But in a new edition of the book, they've just, apparently they squeezed a problem in before those. So notice my numbering might be off from what you have in your book, depending on the book you're using. This is all from the newer book. And so that's what we have. Okay. Now here's another idea. We haven't seen this idea before. Remember, we know the area under the curve is equal to the integral. What these two, well, parts A and B, what this problem says, it says determine visually whether the integral for these from A to B, because that's the function f, notice they both say the function f, determine whether the definite integral of f of x from A to B is positive, negative, or 0, and then express it in terms of A. So what we're trying to find from this picture, we're trying to find the integral from A to B of f of x dx. Now, we know if it just stopped right here, the answer would just be A. We'd say, oh, the area under the curve, that's A. Now, what's interesting, if I take that piece right there, since it's, so this area is A, this area, since it's under the curve, if I do the integral, it's going to be negative A. And think about that in terms of, say, profit. If I was doing profit, and I'm going around here, and here's, you know, here's x is 0, and this is profit. Well, if I'm doing profit and I'm down here, well, I've got a negative profit down here. This area would be the total negative profit I have. And so anytime you're below the x-axis, the integral is going to be negative. So this integral down here is actually negative A. And then this one's above, so again, that's A. That one's above, so that's A. So we actually have A minus A plus A plus A. These two cancel out, and we just have 2A as the total. And so thinking about that the same way for part B, if I've got the interval from A to B of f of x with respect to x, think about that, what that one is. All of those are below the x-axis. So they're all going to be at, the area is A, but the integral is negative A. Area is always positive. But to show that area below the x-axis, we call it negative A. That's what the integral would be. So in this case, the negative is just, the answer is just negative 3A. So we had negative A, negative A, negative A. So of course we had negative 3A. All right, so that's just some nice little pictures to kind of think, okay, what's going on? How does this work? And just as I mentioned in part A, some of that negative profit would counteract the positive profit, and we'd be broken even after those first two. That's why they just canceled out over here. And then up on the top one, we just had positive 2A. Okay, let's use that for this next problem, where once you look at the picture, you'll probably know immediately if the sign's going to be positive or negative. But then we'll actually find the answer and determine what it is. All right, so let me pull another problem up here. And this is about our last problem. We do have one, not our last problem we're doing, sorry about that, but our last problem we're going to pull from here. There is a word problem you probably saw is the next problem that was up there. We'll get to that fairly soon. Okay, so now they give us a curve. Notice it says here we're integrating from 0 to 2. So from 0 all the way to 2. First off, we want to know, do you think you're going to have more area above the curve or below the curve? Is this going to be a positive answer or a negative answer? The question formally says, evaluate each integral then state whether the results indicate that there's more area above or below the x-axis, or that the areas above and below the x-axis are equal. Well, we know this is below, so that's going to be negative. We know this one's above, so that's going to be positive. And clearly we see there's more area above than below, so we're going to end up netting being positive. Let's check. Let's find the integral and show that, hey, is this really positive? Of course it will be. Find it, back up our thoughts. All right, so we've got that integral. So I'm just going to go from here and let's go ahead and do it. So let's see. We know that x squared, go up 1 on the exponent, multiply by the reciprocal. Go up 1 on the exponent, multiply by the reciprocal. And then we're evaluating from 0 to 2. All right, remember what that means. Plug in the 2 for the x. And then minus, and then plug in the bottom number, 0 in this case. All right, so let's see what we have. The 2 cubed is 8 times 1/3, so that's going to be 8/3. The 2 squared is 4, half of that is 2. Minus, keep that bracket there. Well, 0 cubed is 0 times 1/3 is 0. And 0 squared is 0 times a half is 0. So that whole piece went to 0. If I've got a nice polynomial that I'm integrating, and I have 0 that I'm going to plug in, that's always going to go to 0. You need to be a little bit careful, because if that's e to a power, e to the 0 doesn't go to 0, e to the 0 goes to 1. But if you've got a polynomial, you can look easily and see that whole thing goes to 0. You don't actually have to plug it in, as long as you're careful. So let's see. Let's get a common denominator here just so we can add these up. If I multiply this by 3 over 3, that 2 over 1, so that's going to be 6/3. So 8/3 plus 6/3, 14/3 minus 0. So I just have 14/3. That's my answer. And if they wanted to go to a mixed number, they could. They would tell you on the computer what to go to. So let's see. 3 goes into 14 4 times. So it's 4 with 2 left over. It's not a very good 2. Oh, boy, that's better. So it's 4 2/3. If you wanted to go to a mixed number, or if you wanted to go to a decimal, see, now we have to approximate 4.67. Any of those would be fine. Usually on the computer, they're going to leave it here, I believe. But again, I'm kind of guessing. I don't know what all the answers look like on the computer, but notice I have positive 14/3 or positive 4 2/3. That means the net of this, if I just integrated from 1 to 2, I'd get a bigger number than 4 2/3, because that area below the curve from 0 to 1 was below, so that was negative. That took away some of the area. But anyway, we know the net, there's more area above the curve than below the curve because we got a positive number. And let's, in fact, say something about that. Since integral is positive, there was more area above the x-axis than below the x-axis. All right. So that's the gist of that problem. So that was kind of nice. Fairly easy to do. Again, it ties into the problem we had before with the positive and the negative areas. So now what I want to do, let's just do another problem, just a nice, simple, they're not showing us any areas, they're not showing us anything. My book is problem 44. and it just says evaluate the integral from 1 to 2 of 4t cubed minus 1 dt, because notice t is the variable. And so they're just giving us an integral, a definite integral. They're just saying, you know what, evaluate this. Don't worry about pictures. Don't worry about areas under curves. Yes, the area, the answer that we get does represent the area under that curve between 1 and 2, but don't worry about it. Just figure it out. So we will. Okay, so we've got the 4, constant multiple, it stays. Exponent goes up 1, multiplied by the reciprocal. Here I don't have a t. When I have a constant, remember you just put a t with it, whatever the variable is. And I'm going to evaluate this from 1 to 2. Now these 4's cancel out. So really what I have is we'll put a parenthesis here, t to the 4th minus t, evaluated from 1 to 2. Now notice that's right, because if I take the derivative, I get 4t cubed minus 1, which is what I had up here. So remember how I evaluate this. I plug in the 2, so 2 to the 4th minus 2, minus, then I plug in the 1, 1 to the 4th minus 1. And let's see, how far do I want to go? I get 16 minus 2. Can we just call that 14? And 1 minus 1 is 0. Oh, 14. Done. That didn't take real long. That does represent the area under that curve, but it's the definite integral. It's the total change in the function between those two values. Okay, so we're actually, here's good news, down to just one last problem. I'm going to show you an application, show you how this works. Now the problem that I'm going to do, again, I took this out. Let me move that out of the way. We'll set a place for it here. We'll grab that file, and it's just this last one here. It's a nice application. Copy, paste. All right, so here's our last problem. Now it's 61 in the new book. I think it was 62 in the old book. Yeah, it was 62 in the old book. But again, don't worry about numbers. My only point to saying that is sometimes I'll put something in here and you look in the book and you're like, well, that's not the number in my book. Okay, it's probably in there. Even if it's not, no big deal. We still can do it. So don't get too tied up with the numbers and stress out because, oh, that's not the number in my book. Okay. All right, so anyway, it says business increasing total cost. Kitchens to Please Contracting determines that the marginal cost in dollars per square foot of installing X square feet of kitchen countertop is given by C prime of X is equal to 4X to the 1/3. A says find the cost of installing 50 square feet of countertop. Well, remember, if we want the total cost, so this one's saying total cost of 50 square feet. Oh, the total cost, that's the integral from 0 to 50 of the marginal cost. Let's see, we'll say C prime of X dx, and then we'll plug it in. So it's 0 to 50 of 4X to the 1/3 dx. So if I find the area under the curve of marginal cost between those two X values, I'm going to get my total cost. All right, well, let's do it. Remember, the 4 is a constant multiple. It stays. We'll just put that here. The X, I have to add 1 to the exponent. So I'm taking that 1/3 and I'm adding 1, which is really 1/3 plus 3/3, because I need a common denominator. So I'm going to get 4/3. So it's going to be X to the 4/3. And remember, multiply by the reciprocal. And then we don't have to say plus C, but we're evaluating from 0 to 50. Sorry, that 1/3 kind of, let's do that out of the way. Again, these 4's cancel, that's nice. So what I really have is I just have 3x to the 4/3 evaluated from 0 to 50. And when you figure this out, you can do it one of two ways. You can pull out the 3 and say, oh, it's 50 to the 4/3 minus 0 to the 4/3. Or you can leave the 3 in there and say, oh, it's 3 times 50 to the 4/3 minus 3 times 0 to the 4/3. It doesn't matter which way you do it, because the distributive property, you can distribute it in, you can leave it factored out, it doesn't matter. Either way is going to give you the same answer. And so the answer either way, notice that second way, that second part of the whole thing just goes to 0. Either way, it's just 30 times 50 raised to the power. Now, when I do that raised to the power, I actually have to put it in my calculator in parentheses. Otherwise, it'll just raise it to the 4th and then divide the whole answer by 3. So it's raised to the 50, 4 divided by 3. So if yours raises it up as a power and you see that as an exponent, then you can just put 4 divided by 3. Mine doesn't. It just says raised to the power. And then I have to put in parentheses 4 divided by 3. So anyway, make sure you can do this in your calculator. Round it to 2 decimal places because it's money. I get $552.60. And I find it kind of interesting because when I looked in the old edition of the book, the answer they gave me was actually $550.61. Now mine is 0.6047. So I'm not supposed to round that 60 to a 61. I don't know if maybe they changed that in the new edition or not, but maybe they did. I don't know, but I know that's the right answer. So that's the total cost of installing 50 square feet. Now let's go to part B. It says find the cost of installing an extra 14 feet of countertop after the 50's already been installed. Well, so what we're doing here, an extra 14 feet square feet. Well, that's on top of the 50. So now what I'm doing is I'm going up to 64. So think about it. I'm starting at 50 and going up to 64. Now, don't worry about that 50 thinking, but we already put in the 50th foot. If I go from 50 to 51, that would only be the 51st square foot. So by starting at 50 and going up to 64, I'm saying, oh, that's square foot 51 through 64, which is exactly what we're looking for. Similar to what we had before when we went 0 to 50, that 0 wasn't saying I put in 0 square feet, but 0 to 1 was the first square foot. So just a little something to be aware of there. I do actually put the 50, but this represents square feet 51 through 64. All right. So now when I do that, it's the same function. It's still the, where'd my function go? 4x to the 1/3. And so I still get 4 times x to the 4/3 times 1/4 from 50 to 64. Those cancel. So I get, why did I put a 1/4 there? What in the world am I doing? That's what happens when I try to get all slick. So I've got that 4 here. The reciprocal of 4/3 was 3/4. I did remember the 4's canceled. Okay, now we're back on track. So it's still 3, I'll write the whole thing, x to the 4/3 from 50 to 64. Okay, so now I plug in the 64 minus, then I plug in the 50. So let's see. So it's 3, I don't know which way I'll do it. I'll do it this way. 64 to the 4/3 minus 50 to the 4/3. 50 to the 4/3 is actually that last answer, because when I did the minus 0, it didn't do anything. But I'm just going to put everything in my calculator just that way. So I get 3 parentheses, 64 raised to the power, parentheses 4 divided by 3. That would add up here. Yep. Minus 50. Oh, I closed parentheses if I didn't say that. I did. 50 raised to the power, parentheses, 4 divided by 3, close parentheses again. You actually don't have to close the parentheses at the very end of the problem. It'll do it for you. But I get when I plug this in, again, make sure you get this when you plug it in your calculator, $215, and it's 0.395, so 0.40. Let's check to see if the book has the right answer on this one. Let's see, on B, they say 215.40. Huh. So that one they're right to the penny, the other one they weren't. I don't know why. But so anyway, it's finding these definite integrals. Definite integrals we are going to be doing the rest of the semester. So make sure this section of definite integrals you are starting to understand. Oh, I take the antiderivative, I plug in the top number minus, I plug in the bottom number. It actually represents the total change in the function, or graphically it's the area under the curve. All right, but that's the gist of this section. Practice these, get these going, and then we'll discuss more about it if you have questions in the live session. All right, hope that helped you out. Keep working hard and get this stuff. All right, I will talk to you later. Have a great day. Talk to you soon.